Now we're going to talk about one of my favorite reactions, the Hono reaction, in which we take an aryl amine, such as aniline, and convert it to a diazonium. So in this case, we'll take aniline, so an amine and a primary amine attached to benzene, and we'll convert it to the diazonium, which is our N2+. This is a useful reagent for a number of different electrophiles. If we take a look at what the N2+ actually looks like, we have a nitrogen-nitrogen triple bond with the central nitrogen being positively charged. So what we see we need to do is basically take a nitrogen as a nucleophile, which will be the nitrogen of aniline, and make a nitrogen-based electrophile. And we do this with sodium nitrite and HCl. So amines are decent nucleophiles, so what we need to do is make a good electrophile that's nitrogen-based. So we can take our salt here, and so we have the oxygen negatively charged and the sodium positively charged. And we can protonate using HCl one of the oxygen atoms. And we now have made sodium chloride as the byproduct. And so we can take this. We still don't have a nitrogen that's a good electrophile, but by reaction with another equivalent of HCl, we want to use the oxygen that already has a proton attached to it. We again kick out the chloride. In this case, we make a molecule of water attached to the nitrogen where the oxygen is positively charged and the chloride anion is the counter ion. We know water is a good leaving group, so we can take the electrons of the other oxygen, kick it down to make a triple bond to nitrogen and kick out water. So we now have nitrogen triple bound to oxygen in which the oxygen is positively charged. This again has no resonance structures because we would have to break one of the atoms wouldn't be without an octet if we tried to draw any resonance structures. But what we've done now is make nitrogen into a good electrophile. And so we can take aniline and the nitrogen of aniline, attack the nitrogen of this nitroso, and kick the electrons up onto the oxygen. So we now have a positively charged nitrogen with two hydrogen on it, singly bound to a nitrogen that's doubly bound to oxygen. And so again, we still have our chloride counter ion here, left over from when we formed the good electrophile. This has no resonance, but what we can do is shuffle a proton from the nitrogen atom to the oxygen atom. So we've made the nitrogen neutral. We've now made the oxygen positively charged. We can draw a resonance structure here in which the nitrogen becomes positively charged and the oxygen becomes neutral. So what we're seeing is that when doing so, we're getting much closer to the product. We can then shuffle one more proton to the end of the molecule, the oxygen. We can do this, draw this intramolecularly, kick the electrons down onto the nitrogen. And so we've made a neutral nitrogen, double bound to a nitrogen that's bound to a water molecule, and we know water is a good leaving group. And so we can take the electrons of the nitrogen next to the ring, kick down to form the triple bond to the other nitrogen, and kick out water. And this is how we get to our diazonium product. And we make a really good electrophile. And again, the chloride counter ion stays with it until the end.